So we have completed the portion on actinides. Now we'll be discussing the transactinides and their chemical properties. The transactinides are shown in this periodic table. They are actually part of a fourth transition series and starts from the element number 104, that is Rutherfordium, and it goes up to element number 118. Now, some of the first few transactinides, they are experimentally studied, and as the later part of the transactinides are also theoretically studied. Now they have been determined by physical methods, that is by counting in the physics experiments, but for the chemistry experiments it is not possible because of the very short half-lives of some of the later part of the transactinides. Nevertheless, the early part of the transactinides like Rutherfordium, element 104, dubnium, element 105, seaborgium, element 106, hassium, element 108. These have been chemically they have been studied in aqueous medium. Also, gas phase chemistry of these elements has been studied extensively. There is also a gas phase chemistry report of element number 112 recently. As mentioned in this slide, these lanthanide and actinides, they are called as the inner transition series, and these transactinides, they are the part of the transition series. So the chemistry of these transactinides, they follow the transition elements as shown in the next slide. Whether they are really D block elements, now you see from the electronic configuration, titanium, the Z of 22, zirconium, Z of 40, hafnium, the Z of 72, and Rutherfordium, Z of 104. They have a similar electronic configuration, like they have the D2 and S2 type of configuration, all of them. Only in case of the hafnium and Rutherfordium, they have 4F14 and the 5F14, that is the filled F levels are also there. Same also we can do about the +5 oxidation state transition elements like vanadium, which is 23Z, niobium 41Z, tantalum 73Z, and dubnium 105 as the Z. Their electronic configurations, you can see that they are similar, that is D3 and S2 type of configuration is there. And finally, the +6 oxidation state, that is chromium, the Z24, molybdenum, Z42, tungsten with Z as 74, and seaborgium with Z as 106. They also have similar electronic configurations, that is D5 and S1. As will be seen later in this lecture, the second and the third transition series elements are considered as the homologues of the transactinides. For example, zirconium and hafnium are homologues of Rutherfordium, niobium and tantalum are for dubnium, and molybdenum and tungsten are for seaborgium. Now the properties of these early transactinides, and see that these transactinides, their half-lives are mentioned here. Some of the early transactinides which have been synthesized in the last century are given here, like 261 Rutherfordium, which has a T-half of 78 seconds. And all these transactinides are actually produced by nuclear reactions in accelerator facilities. So this 261 Rutherfordium is formed either by a 248 curium target with a oxygen 18 beam, or 244 plutonium target with a neon 22 beam. In both cases, 5 neutrons are emitted. But for these reactions, the cross section is significantly different. For the first reaction, that is the reaction from 248 curium of 10 nanobarn as the cross section, and for the plutonium 244 as the target, the cross section is around 4 nanobarn, and also the rate of production also varies. Even though the product is same, but from 248 curium, the rate of production is much higher because of the higher cross section. That is 3 to 4 atoms are produced per minute. And from the second reaction, that is from 244 plutonium, only 1 atom per minute is produced. Now coming to 262 dubnium, that is element 105. It has a half-life of 34 seconds. And the target required for this is 249 berkelium, where a oxygen 18 beam is used with again 5 neutrons emitted, and with a 6 nanobarn cross section you have the product around 2 atoms per minute, and with a 248 curium target with a 19 fluorine as the beam, you have 5 neutrons are emitted, and with 1 nanobarn, which is a 6 times lower cross section, and that is why the production also is less. You have only 0.5 atoms per minute. For the 263 dubnium, it has a half-life of 27 seconds, and it is produced from 249 berkelium target using oxygen 18 beam with a 10 nanobarn as the cross section with the 3 atoms per minute. Now coming to the seaborgium isotopes, there are mainly 2 isotopes of seaborgium. One is 265 seaborgium, the 7.4 second half-life. For this 248 curium target with the neon 22 as the ion beam, the reaction is done with a 0.24 nanobarn as the cross section, and 5 atoms are produced per hour. For the 266 seaborgium, which has a relatively longer half-life, that is 21 seconds, again the target is 248 curium and the projectile is 22 neon, and 4 neutrons are emitted in this case, but the cross section is nearly 1 order magnitude lower with a production rate of 0.5 atoms per hour. Now the challenges in case of the transactinides is that the production and transport. This is a challenge because, as I have already mentioned, the cross sections are very, very low in the nanobarn, even less than nanobarn for seaborgium nuclides. And also, so what type of nuclear reaction one has to carry out. And finally, efficient detection as well as identification. The detection, it is done by the characteristic alpha decay and the time correlated alpha of the mother to the alpha of the daughter in the decay chain. I have shown that in this diagram here, where you have 263 seaborgium, which is decaying to 259 Rutherfordium. So 263 seaborgium has a half-life of only 0.9 seconds, and this is decaying to 259 Rutherfordium with a half-life of 3 seconds, which is subsequently decaying to 255 nobelium with 3.1 minute as the half-life. So the alpha particles you see are from 263 seaborgium has nearly 50% alpha and 50% spontaneous fission. For 259 Rutherfordium, you have 97% of alpha and 3% spontaneous fission. And for the nobelium 255, we have 62% alpha and 38% electron capture. So ultimately, when you do the counting, the seaborgium as well as the Rutherfordium must have already decayed, and so necessarily you have to count the 255 nobelium. And if you are able to count 255 nobelium, or if you are able to detect it, then you can always assume that 263 seaborgium has formed. Now the experimental challenges, because the production and detection rate is very, very less, this is a very big challenge actually carrying out these experiments. So this is called as a single atom chemistry or atom at a time chemistry. When you carry out the chemical reactions, then you are basically dealing with only one atom at a time. And as I already mentioned, they have very, very short half-lives ranging from few seconds to microseconds. And also there is uncertainty about what time the nuclide is exactly formed. So that is not known. as it is a statistical process. With all this, it is very difficult actually carrying out these experiments, and many times thousands of experiments has to be carried out continuously over a period of several days, and the data obtained are to be finalized after getting the results. Now the requirements in the experimental setup: we need a fast transport and separation system. We also need an online detection system of high efficiency as well as high resolution. These challenges can be met with highly sophisticated automated instrumentation. Now, when we are talking about the transactinides, many times there is this feeling that these are called previously as super heavy elements. So these super heavy elements, or the transactinide as they are known, they are the heavy actinides which are undergoing spontaneous fission, and their half-lives becomes very short. This we know already, that these heavy actinides like lawrencium, it has very short half-life. I have given this table here where this 254 lawrencium, which has a 13-second half-life, and like that it goes on 255 lawrencium, 21.5 seconds half-life, 256 lawrencium with a 27-second half-life, 259 lawrencium with 6.2 second half-life, 260 lawrencium with 2.7 minutes half-life, 261 lawrencium with 44 minutes half-life, 262 lawrencium 3.6 hours half-life, 264 lawrencium 4.9 hours half-life, and 266 lawrencium with 10 hours half-life. So with the exception of 259 lawrencium, you can see that mostly the neutron number increasing, the half-life becoming higher. So on this basis, the transactinides should have much lower half-lives because they are heavier radionuclides. Also, from the nuclear physics point of view, there was prediction that there will be an island of stability predicted on the basis of the cell model at Z of around 114, that is proton number of 114 and the neutron number of 184. So this was predicted much earlier, and subsequent theoretical calculations have suggested that this island of stability may be at a neutron number of around 162 and with a Z value of maybe around 126 or maybe 120. This may give the most stable nuclides. If this is the case, then based on the neutron number, we can say that element number 104, which may be giving a very stable radionuclide. So that means the super heavy elements with the island of stability may start somewhere around even element number 104. So that is, the Rutherfordium can be considered as one of the super heavy elements. So it starts from Rutherfordium, and most of the transactinides, they can be called as the super heavy elements. Now from the nuclear physics point of view, the super heavy elements, they exist mostly because of the cell effects. That is because of the magic numbers, you get the extra stability, and those with a lifetime of greater than 10 to the power minus 14 second can be considered as a chemical element. That means if some radionuclides which are having lower than this as the lifetime, we need not consider them as the elements. So the stability of a nuclide mainly based on the spontaneous fission which is taking place with the heavier actinides or the transactinides, and this is given by a parameter called the fissility parameter, which is defined as Z square by A, where Z is the charge of the radionuclide and the reflection of this proton to neutron ratio. This is also depending on the Z square by A, or the fissility parameter. Now, based on the liquid drop model, you can calculate this lifetime of this, or the decay lifetime for spontaneous fission of this radionuclide. The red line here, what I have drawn now, this gives this calculated line from the liquid drop model, and those which are falling below 10 to the power minus 14 seconds, we call them as non-existent. So that way, somewhere between nobelium and rutherfordium, we find this region with the x value of 0.88. So x is nothing but the facility parameter at z square by a. So with this value, we can say that those elements will be non-existent. However, this is not the case, and we know that these actinides like up to lawrencium are there, and also the transactinide elements were discovered subsequently, suggesting that this cannot be predicted based on the facility parameter and the liquid drop model. So the experimentally determined values suggest that the cell effects are very, very important, and the transactinides are same as the super heavy, or it can be considered as same as the super heavy elements based on this. Now coming to the synthesis of the transactinides, heavy elements beyond fermium, that is Z equal to 100, they are done by the fusion reactions, and before or up to fermium, these are done by neutron capture reactions in the nuclear reactors or by the in-pile reactions. Now there are two types of fusion reactions. One is the cold fusion, where the excitation energy is relatively less, that is the 10 to 15 MeV. So in that case, we use medium to heavy projectiles, that is iron 58, nickel 62. These type of projectiles are used, and also the targets are like lead 208 and bismuth 209. In this case, we have relatively neutron deficient products are formed, and the products have relatively short half-life. The other way of producing by fusion reaction is the hot fusion, where the excitation energy is as high as 40 to 50 MeV, and the target actinides are 248 curium, plutonium 244, etc. And light projectiles such as oxygen 18, neon 22, 26 magnesium, etc. In this case, 4 to 5 neutrons are evaporated as compared to only 1 neutron by the cold fusion reactions. And the relatively long-lived neutron-rich isotopes are formed. The cross sections are from nanobonds to picobonds for these hot fusion reactions, but you have few atoms per minute for rutherfordium and dubnium, but only 5 atoms per hour for 265 Seaborgium. So the schematic of this cold fusion and hot fusion is given here, and this is the compound nucleus formed by a given reaction, that is 58 iron and 208 lead. You have the fusion, it gets the compound nucleus 266 hassium, and it gives out 1 neutron and forms 265 hassium. In this case, we have 5 into 10 to the power 16 projectiles on the target to produce only 1 atom. In case of the hot fusion, we have the curium 248 as the target, and the projectile is 26 magnesium as given here. You have the fusion, and you have the compound nucleus as 274 hassium, and it is giving out around 4 to 5 neutrons to give either 269 or 270 hassium. In this case, we have 1 into 10 to the power 17 projectiles on the target, and we are getting 1 atom. The experimental setup is given here, where you have actually this, the reaction chamber is there, where you have a beryllium backed, this target is there as shown here, and the oxygen 18 beam is coming this way, and this is, that is, whole system is enclosed, and the cooling is done by nitrogen gas passing through this at 0.2 milligram per centimeter square, and this reaction is taking place, and the recoils, whatever is coming out of this nuclear reaction, they are actually transported by the helium gas jet in the presence of aerosols, and this gas gel outlet which is going to the collection site where the experiments are carried out with special experimental setups like Volga or ARCA. Now for the target, because the very large beam current is there, so this target is going to be burnt very easily, So that is why the cooling of the target has to be done. And also we need to have this target rotated. So here one such a schematic is given here, where you have three banana shaped targets, and this wheel actually where it is mounted, this gets rotated and then it gets cooled also, so that at one time one target is only seeing the beam. After that this target is moved, and then the second target is seeing the beam, and finally the third target is seeing the beam. That is how it is rotated, and alternatively we get these targets exposed to the beam. Now the product from the radionuclides are collected in the solution form for the solution phase experiments, and in the gas form for the gas phase studies. Now one important part here is the atom at time chemistry, the single atom chemistry. Now this becomes very vague if you have only one atom, because when you are carrying out the chemical reaction, we know this chemical equilibrium which is given here, that is A and E reacting to give X and Z. So the reactants are A and E. So A atoms of A and E atoms of E, they are reacting to give X atoms of X and Z atoms of Z as the products. And the Gibbs free energy for this is given by this equation, which is simplified to give del G0 equal to minus RT ln K. The problem is when you have a bulk quantity, then it is fine. But when you have only single atom, it can either exist as A or as X. So it can either be in the left side or it can be in the right side. So the equilibrium constant in that sense has no meaning. However, this studies how it has to be carried out. So it has been proposed that such studies can be carried out by partitioning experiments, where the element which is formed, it will be only in one phase. That means if you have a solid liquid partition or even partition between a gas phase also, depending on the type of the experiment, the metal which is formed will be either in one of these phases which are in equilibrium. So which is shown here, this figure shows that the reaction coordinates versus the del G values, and if you see this delta G value, if it is for this reaction mx plus y, which is the reactant, which is the transition state is y mx, and the final product is my plus x. Now whether it will be depending on the mx or my depends on this activation energy, whether the forward reaction is taking place or the backward reaction is taking place, as mentioned here in this equilibrium reaction. Now if the delta G is less than 15 kilocal, then the reaction time will be less than 1 second. So accordingly, this, if you carry out the reaction in a very short time, that is less than 1 second, then we have to find out the conditions in which the delta G value should be less than 15 kilocalories. Another important aspect is the relativistic effect, which is very important for the transactinides or the heavier elements. The relative effect is important, and it has three different types of relativistic effects are there. One is called the direct relativistic effect. Now this direct relativistic effect is thought to apply only to the innermost K and the L cells. However, in case of transactinides, it applies to the outermost S and P cells as well, and that is how these outermost orbitals are also gets contracted. The indirect relativistic effect, this leads to the expansion of the outer D and F orbitals. So for the seaborgium, the level sequence of 7s and 6d are inverted. I have shown here a picture actually where these energy levels are given, and you can see for seaborgium there is really a reversal of this 7s falling below that of the 6d levels. So this is how this relativistic effects becomes important, which decides the chemistry of this transactinide. Now there is a third relativistic effect that is called the spin orbit splitting or the SO splitting, and this is called the third relativistic effect. And this SO splitting decreases with increasing number of subcells. That is, it is much stronger for the inner cells, than that of the outer cells. So each of these are of the same order. Each of these means this, all these three relativistic effects are of same order and grows as z square. That means increasing the charge, it increases these relativistic effects. And this is becomes very, very important for the transactinides. While seeing the chemistry of these transactinides, sometimes you find that it is not matching well with the homologs because of these relativistic effects.